This lesson is about the atomic nucleus, and here are your objectives. The atomic nucleus is made up of both protons and neutrons. Protons are positively charged, and neutrons are neutral. And they have approximately the same mass. Now, because they both make up the nucleus, we call them both nucleons. So a nucleon is a more general term that refers to either a proton or a neutron. Now, the number of protons in a nucleus identifies the element. If you have 6 protons, that means that you are a carbon. You can have different number of neutrons, however, and still be the same element. Those are called isotopes, and we'll talk about those in a moment. A particular species of nucleus with a specific number of protons and neutrons is called a nuclide, and we can identify nuclides, species of nucleus, by writing them in this kind of fashion. The X is replaced by the chemical symbol from the periodic table, for example, He for helium. The Z is replaced by the number of protons. If you're helium, you have 2 protons. Remember, the number of protons identifies the element. And the A is replaced by the total number of nucleons. So the total number of nucleons is the protons and neutrons. Helium has 2 protons and 2 neutrons. Add 2 plus 2 together, you get 4. So we have 4 total nucleons. This number up at the top here is called the atomic mass number. Whereas the number at the bottom, the number of protons, is called the atomic number. To give you a couple more examples, you could have carbon, which by definition has 6 protons, with 6 neutrons. Add 6 protons and 6 neutrons together, and you get 12 total nucleons. You could, however, also have carbon with 6 protons. Again, it always has 6 protons, but with 8 neutrons, and then you'd have a total of 14 nucleons. So these two are isotopes of each other. They are nuclides that have the same number of protons, but a different number of neutrons. Again, nuclides with the same number of protons, but a different number of neutrons are called isotopes. So carbon-12, as we might call this, and carbon-14 are isotopes of each other. This one has 6 neutrons, this one has 8 neutrons. Another example, barium with 56 protons and a total of 138 nucleons would be written like that. And if you do the subtraction 138 minus 56, that tells you that there are 82 neutrons here. Now you might be noticing that the number of neutrons is going up as we get higher in the periodic table, more than the number of protons. Here we had a total of 2 neutrons, then we had 6 or 8 neutrons here, and now we have 82 neutrons, much bigger than the 56 protons. And we'll talk about why that is in a moment, why the neutrons are increasing faster than the protons. Now, to start to think about that, let's think about why the nucleus stays together in the first place. Because if this is a helium nucleus, I'm going to draw the protons in red and the neutrons in white. We said that we've got 2 protons and 2 neutrons in a helium nucleus, and we've got electrons orbiting around. And this is very much not to scale. So these red are my protons, and these white are my neutrons. So we've got these 2 positive protons sitting right next to each other, and we know that by the electric force, the Coulomb force, like charges repel. So these 2 positive charges, the 2 protons, want to get away from each other. So why is the nucleus intact in the first place? Why is it not blown apart by this repulsion? Well, it's because there's another force acting in the nucleus, one that might be new to you, called the strong nuclear force. And the strong nuclear force is actually stronger than the Coulomb repulsion between the protons. However, it's a very short range force, so we don't encounter it in our everyday lives. And it's attractive between all nucleons. So protons attract other protons, neutrons attract other neutrons, and protons and neutrons attract each other, all by this strong nuclear force. In contrast, the Coulomb force, the electric force that is trying to push these 2 protons apart, is not as strong. However, it is a longer range force. It operates over longer distances. And of course, it is repulsive between the protons because they are both positively charged, like charges repel, but doesn't act between neutrons or between neutrons and protons. So neutrons experience the strong nuclear force, and so do protons. Both protons and neutrons are nucleons, and all nucleons experience this attractive strong nuclear force. But protons also experience the repulsion of the Coulomb electric force. So protons end up in both of these columns, but neutrons only in the attractive column. So adding more neutrons adds more strong nuclear force without correspondingly increasing the electric repulsion. In other words, by adding more neutrons, you're adding more of a kind of glue that's holding the nucleus together, this strong nuclear force, without also increasing the repulsion that comes with the electric force between protons. So as nuclei get bigger, you need more glue to hold them together, and that means more neutrons per proton. So here I've drawn a larger nucleus with the protons in red and the neutrons in white, and there's more neutrons than protons because they're trying to hold this thing together with the strong nuclear force felt between all nucleons. However, there's still a limit in the size that a nucleus can become. We don't see nuclei that are stable above a certain size limit. If you consider these protons on opposite ends here, remember that the electrostatic repulsion of the Coulomb force is a longer range force than the strong nuclear force. So these are able to repel each other with the electrostatic repulsion of the Coulomb force, but they're not able to attract each other by the strong nuclear force. They're too far away. And there's just not enough attraction to the nucleons next to them to hold this thing together as the nucleus gets bigger and bigger in size. So we don't see stable nuclei of larger size because of this difference in range between the strong nuclear force, which is short range, and the electrostatic repulsion trying to blow the nucleus apart, which is longer range. We can summarize this pattern of increasing neutron number as we get bigger in something called a chart of the nuclides. So here we have the number of neutrons on the y-axis and the number of protons on the x-axis. So if this is the number of protons, remember that the number of protons identifies the element, so you could imagine having hydrogen, helium, etc. going to the right across here. By the way, just a note that sometimes you'll see these reversed with the number of protons on the y-axis and neutrons on the x-axis. Now, what we're going to graph here are the stable nuclei that don't decay into something else. And if the number of protons and neutrons were equal in stable nuclei, then the graph would lie along a line that looked like this. This line is meant to indicate that the number of neutrons, n, is equal to the number of protons, z. However, we don't see that. What we see instead is that the graph is along the line at the beginning and then curves upwards. In other words, down here for small nuclides, we have the same number of neutrons as we have protons, but up here we have more neutrons than protons. Again, because the neutrons are providing this glue to hold the whole thing together. To give you some examples that we looked at earlier in the video, remember that helium had 2 protons and 2 neutrons looking like that, whereas moving further to the right, barium, which had 56 protons, we saw had 82 neutrons, giving it a mass number of 138. So it would lie along the graph somewhere up here. Just one more thing, if this is the line of equality where the number of neutrons is equal to the number of protons, and these are the stable nuclides, that means that up here, these are unstable nuclides in this region, and because they are further to the top of the graph, they have too many neutrons for the number of protons that they have, and therefore they can achieve stability by turning neutrons into protons, and that's actually possible by a process called beta minus decay, and we'll see that in a future lesson. Whereas down here, below the red graph, these have too many protons. They are further to the right than they should be for how far up they are. And therefore, they can achieve stability, move closer to the graph by turning protons into neutrons. And that's possible by a process called beta plus decay, or by a process called electron capture. And we'll look at these processes in future lessons. But just to relate them to this chart of the nuclides, if the number of protons is going up as you go to the right, and the number of neutrons is going up as you go up on the graph, then over here we have too many neutrons, we're too far up. To get to stability, we want to turn neutrons into protons. Over here we have too many protons, so to get to stability, we want to turn protons into neutrons. And again, we'll look at those processes in the next lesson. So that's an introduction to the atomic nucleus and the chart of the nuclides.